I'm Ranger Kathy Taylor here at Paris Mountain State Park in Greenville, South Carolina. I'm sitting alongside Mountain Creek. Lots of fifth graders come to the park and help us determine the water quality. When they come to the park, they are our scientists for the day. We call them ecologists, looking at the homes. Eco means home in Greek. Looking at the homes here and determining if we have good homes, and that includes water quality. We expect good water quality because we have a forest around the creeks and the lakes here at Paris Mountain. But we get to find out for sure from the students, and we've had issues at times, so that's good to know. So to determine the water quality, students will be measuring the biotic and abiotic parts of this place. Biotic being the animals they catch in the creek, and the abiotic part will be the temperature and pH of the water. So we know what temperature is, I bet. What about pH? What is that? That's measuring the acidity of the water. When fifth graders come here, they use pH strips and a pH chart, and they dip the pH strip into a bucket of creek water for about 5 seconds to saturate the strip, and then they actually lay the strip down for about a minute, let it process, and then they compare the colors on the strip to the colors on the pH chart. So it's really color matching. So when they do this, they know that on a pH chart, the lower the number, the more acidic the pH. The higher the number, on a scale of 0 to 14, by the way, the higher the number, the more alkaline or basic. We'll say the word basic. It is really means more hydroxide ions are in the liquid in that case instead of hydrogen ions. But right at 7, right in the middle there, is what we call neutral, equal numbers of hydrogen and hydroxide ions. But it's what we can say is that it's good water to have in the creek for good water quality. Any animal could live in good water quality water, like with a 7 pH, but many cannot live with a lower or higher pH. When we measure pH, we're really talking about the acidity, right, of a liquid. And so we're going to measure 5 liquids, the pH of 5 liquids that were easy to find around school or home, and just gives you 5 examples of pH and how much it can vary, really. That's kind of fun to try different substances. So let's think a little more about this experiment we're doing here with pH. We have variables, and so we can say we have dependent and independent variables as well as controlled variables. That's talking like a scientist. And we know that the pH is dependent on which liquid we use. So it's the dependent variable. It depends on which liquid. The liquid is independent. And as for controlled variable, we're using 50 milliliter beakers, and we put 30 milliliters of liquid in each beaker. So we have the same amount of liquid. That's the controlled liquid. So we have pH is the dependent variable, the liquid itself is the independent variable, and the 30 milliliters in the beaker is controlled variable. Hopefully you have a sheet that you can use to help do this activity with me as we're scientists together. And I wrote down on the first line the 5 samples, 5 liquids that we have with us today. And you can do the same on your sheet. So the first liquid, sample 1, is detergent, as in laundry detergent. Then we have bottled water, just water that you buy that comes in a bottle already. We have orange juice, or OJ. We have soft drink, like soda, or whatever you call that drink, the fizzy drink that you drink, soft drink, and milk. So we said we have those 5 written on our sheet. The next part of this will be to predict, to use what you already know about these liquids, since they are kind of commonly used liquids, what you might know to determine, to predict the pH. Make a prediction. How are we supposed to do that? Well, we're scientists, and scientists have tools to use. We can ask questions, that's a tool, and we can make hypothesis statements based on what we do know about these liquids. So, a hypothesis is an educated guess that can be tested. So let's look at these liquids. How about orange juice? Have you ever noticed that fruit juices can cause your lips to sting a little and water doesn't do that? We might ask the question, since fruit juices cause our lips to sting and water does not, could that be because fruit juices are more acidic than water? And then we can sound like a good scientist and make a hypothesis statement saying fruit juices are more acidic than water. Now, to find out if that's true, we're going to measure the pH, right? Well, let me give you another statement that I've read somewhere. I've read that alkaline solutions, that is those with a high pH number, are good at tackling dirt and grease, whereas acidic solutions are good at cleaning metal. All right, so if we can believe that, let's see how we might apply that. Which of these 5 liquids that we're going to measure today are used to tackle dirt and grease? Is it detergent, bottled water, orange juice, soft drinks, or milk? Okay, hopefully that's going to help you make a prediction. As for cleaning metals, I've heard that soft drinks are good for cleaning metal. If you didn't know about that, just try putting an old beat up penny in a glass of soft drink overnight and see what it looks like in the morning. So we can use what we know already, and we can ask questions, we can make statements and determine if they are true. And in this case, we're going to do that by measuring the pH next. And the next step will be to actually find out using pH strips. And so the chart we're going to use is actually on the box, and we're going to try to, turning it the correct way, we're going to try to determine the pH of each of these liquids. So let's get started. I'm going to put a pH strip in the detergent. We have 50 milliliter beakers here with 30 milliliters of the liquid, trying to keep things consistent. So we will take this strip out, lay it down. Going to put it in bottled water as well for about 5 seconds so it's fully saturated. Take that out. And then OJ, orange juice. Are you getting thirsty? It's looking at some of these. So, soft drink. Not getting any green on some of these. That's interesting. And then milk. All right. So, let's find out. We've had a little bit of time for each of these to process. And I'm going to take the strip for detergent. And I'm going to start, I think, with the 0 to 7. It just sort of makes sense to do that. And first of all, I'm noticing some green. I usually try to start by looking at the green. 6 and 7 have green on this chart. Let's look at 7 through 14. 7 appears on both sides of the box. And try to determine what it is closest to. Looking at green first, and then look at all 4 of the colors. So you determine that. You're the scientist today, and write that down on your sheet for the 3rd row. Like for sample 1, you had your predicted pH, and write down what it actually was. So now let's look at the bottled water. And we'll look at a pH strip here. Let's see, I said I wanted to start with 0 to 7. Then we have the green, so we're looking at 6 or 7, or we can turn this to look at 7, 8, 9, 10, 11, 12, 13, 14. So do you have an idea of which it's closest to? What's the best match? All right, if you do, write down that number for bottled water, sample 2. Let's do orange juice. Oh, no greens here. Okay, we're not even going to fool with the 7 to 14 because there's no green showing. So let's see. So not 7 or 6, one of the others. So just looking at these colors, try to get the best match for these. Trying to see what will help us see it best. What do you think? Write down the number you think matches best for the orange juice, which is sample 3. All right, soft drink. Let's look at this strip here. Okay, this is interesting. We see no green, so we're working with 0 to 7, and we're actually seeing a sort of a pinkish purple color that we hadn't seen in the others. So let's take a look here. We're talking about one of the low pH numbers, very acidic numbers. Is it 0, 1, 2? You determine, maybe looking mostly at that pinkish purple and then looking at the other colors too. All right, that's a soft drink. Finally, we have milk. Write down that soft drink one for sample 4, what the pH number turned out to be. Now we'll look at milk. We got green. And with these 0 to 7 side of the box, we have 6 and 7, both have green. So see if that looks good. You can also look at 7 to 14 over here. See if there's another shade of green that matches better. Okay. You have your number. Write it down for sample 5, milk. Were you surprised at any of the results? You know, we definitely had some acidic substances here. Did we have any that were above 7? Nothing really high on the chart, but of 0 to 14. But we did get some that were above 7, I believe. Did you agree? So on your sheet here, you can use the line graph to write down the pH numbers for various liquids, like whichever one might have been 0, 1, 2, 3, for whichever number it was, write down the name of that liquid below the number. And then maybe for the next highest number, write down the liquid and on up. We didn't have anything over here, but write down the number for each of these liquids. So why are we interested in pH? We already said a little bit about that, but we know that understanding the pH in a stream or a forest helps ecologists to know more about the relationships between the abiotic and the biotic parts of that place. We expect good water quality at the park, at Paris Mountain State Park, because we have a forested area that drains into the water. So the land that drains into the water is forested, so we call it a forested watershed. And what does a forest do to help the water quality? Well, you've probably seen what happens when it rains hard on bare soil. You get a muddy runoff, you get all sorts of stuff, any pollution going straight into the water. But with the forest soaks up water like a sponge and slowly releases it after pulling out pollutants before it gets into the creeks or lakes. Well, now you know how to measure pH using pH strips and a color chart. There's various ways of doing this digitally as well, but scientists do need to find out about how a place works. Ecologists in particular look at these living and non-living parts of a place and how they interact together. And the more we know about the way our world works, the better we can take care of it, the better we can appreciate it and enjoy being in the great outdoors.